Professor Pavel Yutkin.
Yeah, I'm
Professor
here.
Pavel Yutkin. Hi, Professor Yutkin. Yeah. Okay, so
Right.
Professor Yutkin is from uh, Harbin Institute of Technology in China. He received his bachelor degree, master degree, and master degree in applied mathematics and physics, and a PhD degree in mathematics and physics from Moscow Institute of Physics and Technology, MIPT. From 2014 up to 2022, he had been working as a senior research associate at the Institute for Computer-Aided Design of the Russian Academy of Sciences and as an associate professor at MIPT. Since February 2023, Pavel Yutkin is a professor at the Harbin Institute of Technology, International Center for Applied Mathematics, School of Astronautics. He has published more than 40 papers in peer-reviewed journals such as Physics of Fluids, Shock Waves, and the International Journal of Multiphase Flow, and regularly contributes to international conferences. He was elected in 2019 to the board of directors of the Institute for Dynamics of Explosion and Reactive Systems as an international recognition of his work. The area of his expertise is computational fluid dynamics of compressible flows. His research includes a lot of problems with high-speed one-phase or two-phase compressible inert or reactive flows using high-performance computing. Professor Yutkin has developed new numerical methods for the solution of hyperbolic systems of equations and applied them to study a number of fundamental and practical problems in the fields of aerospace engineering and explosion safety. He has more than 15 years of experience in both academic research and in the development of software for industries. The title of his presentation today is Numerical Study of a High-Speed Collision of Metal Plates Using a Multiphase Model. So Professor Yutkin, please go ahead.
Many thanks for your introduction. It looks like that these conferences are a very good place for Russian international scientists for meeting, maybe better than some places in Russia, I believe. So this work was carried out and is carried out with the collaboration of my former PhD student, Petr Chuprov, and with Svetlana Fortova from my former Institute for Computer-Aided Design of the Russian Academy of Sciences. Uh, the high-speed collision of metal plates is the underlying fundamental process for such technology as explosive welding. Welding technique has wide applications in areas such as aerospace technologies, automobiles, shipbuilding, bridges, and many others. It is one of the important manufacturing methods in industry. High-velocity impact welding is a kind of solid-state welding process that is one of the solutions for the joining of dissimilar materials that avoids intermetallics. And high-velocity impact welding is characterized by a low welding temperature and fast welding speed. The process is conducted at room temperature. And furthermore, there is no external heat input during the welding process. So this figure illustrates some basics of the mechanism of explosive welding. For many years, different aspects of the mechanism were not clear, and actually, it is shown even now. Actually, you can see here the schematic of the formation of wave process that provides the explosive welding. After the transient force is applied on the external surface of the flare here, the flare moves towards the target at the velocity of several hundred meters per second. As its name suggests, explosive detonation is implemented to provide the impact force for the flare. When the flare collides on the target, a jet, this one is generated at the collision point, which contains contaminants, oxide layers, and a thin layer of metals. So as a result, this jet provides cleaning and preparation of the surface of the plates. And with the transient force, there are brought they are brought within atomic distance where the atomic bond is formed. This is a very fast process. This process usually takes several to dozens of microseconds based on different welding processes. You can see here that there are two main general schemes for explosive welding. This one is called inclined scheme, and this one is parallel. And the inclined setup came from the idea of hollow charge. It was used earlier than parallel setup. And alpha is the initial angle in the inclined mode. The problem is that this scheme is not capable of handling large sheet metal, and the parallel setup was developed later and was mainly used to weld large plates with a predetermined standoff distance. Actually, this explosive welding technology is well-established technology, and it was used. It had been used for many years. However, despite the considerable history of studying, uh, there remain a number of fundamental issues that hinder uh, the effective usage of this technology. Significant gap is observed in the study of the shock compressed gas, which is formed between the metal plates being welded, and it's influenced on the welding process. I mean, the flow of gas in this gap during the explosive welding. For a certain time, it was believed that the gas between the colliding plates could not play any significant role in the formation of the welded joint. But as I said, the number of investigation about this subject is limited, and it turned out that this is not so for industrial production technology for large B metals. Experience with the production of large plates by explosive welding shows that the gas in the welding gap has a controlling effect on the process of formation of welding joint. For example, it was shown that the replacement of air by some inert gas provides joint of high quality. However, the role of this shock compressed gas uh, has not been studied sufficiently. Generally speaking, the shock compressed gas has two effects, both positive and negative. On the other hand, it also cleans and prepares the surface of the plates unless a jet of oxides and contaminants is formed. I mean that this shock compressed gas also provides the cleaning of the surface of the plates that will be welded. On the other hand, the gas moves at hypersonic velocities. Its ionization occurs. It blows metal microparticles away from the surface of the plates, and it can lead also to melting of the metal plates. You can see here a picture from this paper, typical negative effect of this shock compressed gas on the welding of metal plates. You can see a typical hole due to this process. This is, for example, a magic box to compare the scale of this big hole. There are a few known works, both experimental and numerical, in which this effect was studied. For example, in this work of Chen with co-authors, they studied the influence of this interlayer on the effect of explosive welding, and they have shown that depending on the thickness of this interlayer, different modes are possible. And they also studied the air shock wave. They used a simplified piston model to predict the properties of this air shock wave. This paper also contains some analytical approach to predict the properties of shock compressed gas based on the aerodynamic theory of supersonic flow around bodies. So this theory was applied to predict properties under some assumptions, of course, of this shock compressed gas. This work of Chinese authors, they also proposed a theoretical model for shockwave propagation. And they have shown that this shock compressed gas can push up the tail of the cladding plate before the collision point of explosive welding. And therefore, this effect is the primary reason for the failure or quality reduction of the welding of long and large plates. And also, I can mention this recent paper of Russian scientists from Volgograd. This paper describes a thermocouple method for measuring the heat flux from the shock compressed gas. That is, they measured the heat flux from this shock compressed gas to the plates. And they have shown that at distances of about 0.5 meters from the beginning of welding, the heat flux is independent on the contact point velocity in the range of several thousand meters per second. And that's it. Actually, there are a few works available on this topic. And in works where some theoretical predictions are made, some simplified models for the formation of shock compressed gas are used. So in my report, I'd like to share my experience in the adaptation of multi-phase compressible model for the simulation of this process. And I'd like to explain some difficulties, pros and cons of this approach for the solution of this problem. The statement of the problem follows the full-scale experiments from this paper of Russian scientist Yakovlev. It was not explosive welding. The conditions were not sufficient for that. However, he considered impact of lead plate on the steel plate, and the velocities were about several hundred meters per second. He used inclined scheme of the impact. And after experiment, he separated the plates and saw crater-like splashes on the surface of lead plate in the direction of the steel plate. And he tried to explain this phenomenon from point of view of the development of Rayleigh-Taylor instability on the surface or on the interface of the plates. And first of all, we considered one-dimensional statement approximately resembling the full-scale experiments. Of course, the process is not one-dimensional, and I will show the multi-dimensional effects because after one-dimensional case, we considered two-dimensional case, that is the inclined impact. And before that, we also considered and carried out three-dimensional pure gas dynamic simulations. We solved all the equations, but with the stiffened gas equation of state, and we tried to get this instability of the contact surface, crater-like instability. But today I'd like to tell you about this statement and this statement. So for the multi-phase model, we consider three different phases: steel, lead, and air. Of course, the one-dimensional problem itself is a canonical one. I mean, you can find the solution using Lagrangian formalism in many books, such as Mader book and so on. So it's not the problem itself. The main problem is to understand the difficulties and specific features of replication of multi-phase model here. I would like to build a robust shock capture and diffuse interface approach that will provide robust simulation of the process without explicit consideration of interface boundaries. That is why we consider both we consider three phases: air, steel, and lead. And then just the same, but with the non-normal impact, with this 5-degree angle of inclination. Mathematical model is based on so-called Byron-Rosetta-like equations. These equations were derived in 1980s for the problems of deflagration to detonation transition in heterogeneous explosives. And initially, this model was for two-phase mixtures. That is some sort of solid phase or explosive and gaseous phase, such as ambient air plus products of combustion of the explosive. But later, this model was developed for many other applications of compressible two or multi-phase flows. the great disadvantage of this model is that this system of equations is hyperbolic. It means that it's possible to provide, of course, there are many difficulties, but it's possible to provide to build very robust numerical methods for simulations of problems even with explicit interfacial boundaries. But the main problem is that this system is not conservative. It couldn't be written in the conservative form because of these so-called Noslin terms that contain derivatives of volume fraction of our phases. Defining system of equations comprises mass, momentum, two momentum equations because it is written for the two-dimensional case, and energy equations for each phases. A stands for air, S for steel, and L for lead. And also the system should be supplemented by some equations that provide the entropy inequalities. And in the original paper, they proposed to solve advection equation for volume fraction of materials. And so each phase considered to be compressible, and generally speaking, each phase has its own density, velocity, and pressure. And but there is some relaxation procedures. I will talk about. I will talk about it later. This is the sketch of the media according to this model. So each liquid volume consists of three phases with their own set of parameters, and we can think that there are explicit interface boundaries inside each liquid volume, and also some interfacial parameters should be assigned, and these interfacial boundaries. So the model that we use generally follows the works of Sorrell with co-authors. They further developed the original paper of Byron and Teata. And also in the right-hand side, you can see the terms responsible for velocities and pressure relaxation, because at some stage of the numerical algorithm, we should provide that these interfacial boundaries are in equilibrium after a non-equilibrium step. So there are many difficulties in numerical solution, even in mathematical formulation of this defining system of equations, because in contrast to Euler equations, there are weak solutions for the Euler equations. Even the mathematical formulation of weak solutions is not straightforward for this model. And strictly speaking, we should add some additional conditions to choose which weak solution we would like to get, and so on and so forth. And so there are many different classes of numerical methods to solve this system of equations, depending on what type of solutions we would like to get. But nevertheless, the beauty is that all this could be done inside one framework of this system of equations with the clear, terms, and the efforts of different scientists in this field could be, joined together and compare with each other. It's a very important thing. As for numerical method, there is so-called strength splitting approach. First of all, a hyperbolic step is carried out, then velocity relaxation stage, and then pressure relaxation stage. What does it mean? It means that at the hyperbolic step, all phases can move with their own velocities and pressures according to the conservation laws. And on the stages of relaxation of velocity and pressure, we should provide the equilibrium conditions of these interfacial boundaries. We can provide stiff relaxation and non-stiff relaxation. In this work, we use stiff relaxation. So these relaxation stages implies the solution of the ordinary differential equations for a vector of conservative variables using PV and PP terms, and these terms stand for velocity relaxation and pressure relaxation. So it's a little bit, so these stages are quite, standard. So if you know how to solve this class of equations, you can find the description of these stages in many actually papers. There is nothing new here. But the problem is here because we would like to solve not two-phase but three-phase problem. And in this case, the formulation of Riemann solver is not an easy problem. And for the problems with explicit boundaries, it would be great to have Riemann solvers that do not smear too much these explicit boundaries. And on that way, only not many classes of methods are suitable. So one of the best is so-called HLC methods that came from methods for the Euler equations, have 10 lux, one layer contact. But it's not easy to generalize it, first of all, to the for the Byron-Nuzat equations, and for the second, for the multiphase model. So we adopted a so-called three-wave HLC solver. It means that if we would like to consider the full Riemann problem for this multi-phase problem, there would be many states, intermediate states, many waves. It's almost impossible to consider all these intermediate states explicitly. That's why a three-wave solver considered just three waves for all phases, just right wave, left wave, and some contact wave, and the speeds are defined using all the phases. And then we used almost common HLC solver, and also this contact speed is used for the approximation of non-conservative terms, because the property of the numerical solution depends strongly on the approximation of these terms. So the approximation of these terms should be correlated with the numerical fluxes in use. I have not much time, but I'd like to say that I have experience in simulations of similar of the application of similar class of models for the simulation of particulate for the particulate flows with particles, and it's not verification, but just related studies that this very similar class of models could be used for simulations of interaction of shocks with particles layer. So we consider the problem of interaction of a shock wave with a layer of particles on the surface, and we compared our simulations with the experimental data and obtained good agreement, including the oscillating behavior of the pressure curve. And one of our recent paper, it's not about this topic, but the model in use was very close. We consider the also problem with gas and another very dense media particles, and the flow was supersonic, and there were explicit boundaries. And the idea was to explain the dynamics of wave propagation inside the layer of particles. And we were able to explain the dynamics of this granular contact angle and transmitted compaction angle when shock wave propagated ahead of layer of particles. So just for you to know that similar class of models can be used for the simulations of dense flows with particles, but closer to our problem. So I'd like to show you simulation results for one-dimensional case and two-dimensional case. So how many time do I have? 10 minutes? 5 minutes?
You have 7 minutes.
7 minutes, okay. So for one-dimensional case, you can see that initially after an impact, you can see two shock waves. This shock wave that propagates to the free boundary of the steel plate, and the shock wave propagating to the free boundary of the lead plate. Interesting thing that we compared the simulation using HLC method with the simulation using HLL method from this paper, very famous paper. And actually, this is one of the first very robust numerical method for the solution such class of problems. But the problem is that it's very snarky. As for the shock waves, it is known from just gas dynamics, from the principles of construction, that HLL method and then HLC method gives almost the same result. But as for interfacial boundaries, you can see that HLC method provide significantly better result in contrast to HLL method. Then the shock wave comes to the free boundary of the steel plate and reflects in the form of a rarefaction wave. And then this rarefaction wave propagates to this interfacial boundary between the plates. The goal of this simulation was to define the acceleration of the interfacial boundary as a result of propagation of refraction waves through this interfacial boundary. Then it's possible to estimate if it's possible the development of Rayleigh-Taylor instability development on this surface, following the original experiments of Yakovlev. You can see that as for refraction waves, say HLL method is significantly worse than HLC method. You can see that HLL method provides actually very bad approximation of refraction wave here. Maybe some average location is okay, but the profiles of pressure are totally wrong. And then you can see the reflection of the shock wave from this free boundary of the lead plate. And then these two refraction waves, they meet somewhere here, and you can see the lowering of pressure. And so the process of propagation of this refraction wave through the interfacial boundary. And once again, the beauty is that this is the diffuse interface method shock capture. We do not need to fit in some boundaries and so on. For these simulations, of course, to get quantitatively reasonable results, we should calibrate our equation of state, and we use the simulations using a wide range equation of states for metals from Joint Institute of High Temperatures, Institute of Professor Kiverin from previous talk. And actually, it's possible to use not, so you can see that we use very simplified Stephen gas equation of state. It's possible to calibrate these constant to get reasonable quantitative parameters in some range that define our problem. But of course, it's also possible to use Migronizing equation of state inside this Baranuzata model. So that's not a big problem. And so we can use real equation of state. This plot demonstrates the acceleration velocity of the interface. This is the acceleration, the orange curve, and this is the velocity of the interfacial boundary. And you can see the very rapid acceleration of this interfacial boundary when a refraction wave propagates through it. So we got the acceleration of the interfacial boundary from lead to steel plate. And the density gradient is directed quite contrary. So these are the conditions for the formation of Rayleigh-Taylor instability. And so actually, this is a possible mechanism indeed for the formation of splashes on the surfaces of the plates when we separate them after the impact process. And the last slide is about the two-dimensional statement. So the statement is just the same. Of course, you can see it's very, very small scale. Of course, it's not for molecular dynamics, right? But it's also a small scale statement. If we would like to move towards shock compressed gas and simulations of this process, we should consider much more long plates and bigger times. Nevertheless, in comparison with the previous result, we just changed this angle and considered not normal impact. What we can see, first of all, the process is significantly non-one-dimensional. We can see that the shock waves are, curved. At the same time, the absolute values of pressure here and x component of velocity here are in reasonable agreement with one-dimensional simulations. But at the same time, you can see a very big velocity in the y direction, an order of magnitude as the horizontal velocity. And you can see here the volume fraction of air. So it means that indeed the model provides the displacement of this air from the gap between the plates. And you can see that this air obtained the speed of the lead plate. Of course, it's not the shock compressed gas because the velocities are too low. Nevertheless, the model provides the reasonable behavior of these three phases in multi-phase flow simulation. Well, I think that I'm almost finished. Yeah, so the main idea is that we try to adopt the multi-phase Byron-Zeta-like model for the simulation of high-speed collision, and also adopt the known HLC method for that. And we hope that this model and approach provide us full-scale simulations and study the process of shock formation in the gap between these colliding plates. So thank you for your kind attention. You can find my contacts. I'm free for collaboration, for answering questions, and so on. Actually, I was going to come in person to university, but unfortunately, the conference is fully online. But even this time, I was ready to come to you and meet in person. So thank you so much.
Thank you very much for the great presentation, Professor Yutkin. You're welcome to come to the campus anytime. We would be happy to have you here.
Okay.
Yeah. So, yeah, well, I look forward to talk to you or have more communication with you later. Yeah. So, do we have any questions in the audience? Professor Yutkin, I have one question. What is the main advantage of explosive welding compared to traditional welding? Like, why do we want to use this technique?
As far as I understand, there are some cases when, for example, if you would like to provide huge sheets of metals with two different properties, and maybe some other technologies cannot provide you to do that.
Okay.
Or, for example,
Okay.
some cylindrical samples. Once again, maybe if we want to use the metals with different properties inside and outside this cylindrical sample, you also can use this technique.
I see. I see. So, okay, Professor Kevin.
A short question, Pavel. Hello, nice to see you. As I understood you on this slide, you were speaking that the velocity of the gas is exactly the same as the velocity of the lead plate. But didn't you catch the cumulative effects in these conditions, or there should be another conditions to see it?
Yeah, I think actually these boundaries are free, and so we should consider the much longer plates, and the speeds maybe should be higher. So in this statement, it was just a very low piston that pushes the gas ahead of it actually. So
Oh, it is a low speed.
yeah, in comparison with these shock processes, the speeds here are low. But here we just follow the statement of the full scale experiment. But of course, there are a lot of many experiments we should move forward with that with high velocities.
Okay, see, thank you.
Professor Yutkin, I have one more question. So, this model seems to be very complicated to me. So I wonder how is it implemented? Is it through standalone code or through commercial software or any or some other approach?
As far as I know, there are no commercial software with the implementation of this model, and that is why actually we should not rely fully commercial codes and so on. It looks like a little bit complicated, but in fact, as I said, the beauty is that all the components are almost standardized. It means that when you try to simulate two-phase flows, the biggest problem in comparison with just gas dynamic flows. For example, Professor Kiverin did not explain the equations and the numerical methods because actually almost everybody understands. It's just Navier-Stokes equations and one or another Riemann solver, and everybody in general understand how to do that. When you try to do two-phase simulations, the problem is that there are many different two-phase flow models, and almost impossible to use the same two-phase model as somebody else. But it's not so for this type of models, because it is very well developed, and if you spend some time, you can get exactly the same results and understand how to do that.
Okay,
but it's in-house computer code.
Got it. Yeah, thank you very much. Because I do quite some finite element simulations, and sometimes I also develop some like user subroutine code for those. So I'm quite curious about this. Yeah, but thank you very much for your answer.
Okay, thank you.